Good day, stats students. So today we're going to talk about section 2.2. We're going to make some graphs for data. And so do not underestimate the value of creating a graph. All right? Even the most powerful statisticians who have all the tools of the trade make use of graphs. Everybody makes graphs to look at the data, to understand it better. And so do not underestimate the value of a graph. All right? So we're going to separate these into two categories. We can make graphs for categorical variables. Okay. Now, what you're going to see in Chapter 2 is that you're going to see various lists, and then you're going to need to memorize these lists. This is the first list, okay, and it'll be very beneficial to you, especially when you take your exams. So, what are the graphs for categorical variables? We can go ahead and either make a pie chart or a bar graph. So please memorize that. Okay. Now you've all seen a pie chart and a bar graph. Okay, but let's go over them and each one, make sure. All right. So a pie chart uses a circle and then goes ahead and creates slices of pie for each category, and then a bar graph uses a vertical bar. Okay, or vertical bars, I should say. All right. So pie charts. So this last point here, because I've already gone over the first two, the size of each pie slice is proportional to the percentage of observations falling in that category. So in other words, if we went around the class and said, okay, what's your favorite color? And 20% said pink. Well, we would represent then 20% of the pie is pink, right? And so that's all that's saying right here, all right? But this is also giving you an idea how we analyze categorical variables in the future. All right. When we get to more sophisticated techniques, if you will, throughout the semester, and we run into data that's categorical, how we're going to analyze that stuff is either with a percentage or a proportion. Okay. So when you have categorical data, that's how we're going to analyze it, either with a percentage or it's supposed to be an or a proportion. All right. And so the pie chart gives us a clue on that. So here's our table from back one section, all right? And so we're going to change this into a pie chart. So we've got 20, 30, 40, and 10. So, here's the thing is that, maybe in the past you had to make a pie chart. We're not going to make you make a pie chart, okay? The computer can make a pie chart for us, okay? What's important is that can you interpret the pie chart? Can you interpret the bar chart? Can you interpret any graph that we talk about in Chapter 2? Okay, that's important. Okay, and it's all about the interpretation. All right, we'll allow the computer to do all the manual work. Okay, so it looks like, boy, we have mostly juniors. The least amount in the group looks like seniors, and that's confirmed by these percentages over here: 40%, 10%. Right? Okay, how about a bar graph? Again, it's for categorical, vertical bar. Okay, now the height of each bar represents either counts, which we've been calling frequencies, or percentages, or if you will, you can put a relative frequency there, proportion. It just depends on what you want to display. All right, but it's the height of the bars. So here's an example of the data that we were just talking about. All right, now notice here I put frequency over on this axis, and if I was in class, what I would show the students is that I'm going to put an arrow right there. Okay, now this program didn't do that, but that's okay. We're going to put an arrow there. What does the arrow mean to you? Is that it's a number line, and that number line just kind of keeps on going, right? Can anyways. I would not put an arrow down here. Why? Well, because this is meant for where the data, the different groups of the data goes. And so what do we have? We have freshmen, sophomores, juniors, and seniors, right? So we're not working with numbers down here. So the values or the categories of your variable are always going to go on this axis down here. Well, since we're working with categorical data, it's going to be groups, right? It's going to be the freshman group, sophomore group, so on and so forth. And then we would read it, right? We got 2 in this group, we got 3 in this group, we got 4 in this one, we got 1 in this one. Well, we could also go ahead and change this over to relative frequency or proportion, right? And so notice now you have 0.4 0.4, 0.3, 0.2, 0.1. All we did was divide through by the total number of people that we took a look at with the frequency, and we get our relative frequency, or proportion. All right. So notice, did the graph change? Graph doesn't change, other than the fact that we changed the axis over here. Okay, and so when you go from frequency to relative frequency, and then if you go to percentage, doesn't change anything. It doesn't change the heights of the bars here. Okay, and it shouldn't. All right. Now, the one thing that I do want to point out is that whenever you make a graph, okay, bar chart, and even some of these other graphs that works with these axes, this axis down here should start at 0. If you don't start at 0, you can make a graph that is misleading at that point. Okay, so you don't want to start at, like, say 100 and then go to 101, 102, 103, 104. That would distort the graph. You should always start at 0. Okay, and once you start at 0, it shouldn't distort the graph at all. All right. All right. How about graphs for quantitative variables? So now our variables is producing, now we have data that is numbers, right? It's quantitative, quantity. Okay, so there's a little slightly larger list here. Okay, and so we have histograms. Again, a list that you should memorize. So for quantitative variables, what kind of graphs should we look at? We can either look at a histogram, stem and leaf, a dot plot, or a box plot. Now, today we're going to look at the first three: the histogram, stem and leaf, and dot plot. We can't get to the box plot today. We have to actually talk about other things. But once we talk about those other things, we'll talk about a box plot. But it certainly belongs in this list. Okay. So here's a histogram example. So we have the following data set represents the time in minutes taken to commute from home to work for 20 workers. And so here's our data. Okay, construct a histogram. So now, if we were in class, what I would say here is that this is going to look like a bar chart, other than the fact that now I'm going to put an arrow down here. Why? Because remember, now keep this in mind. Always keep this in mind, because this is students a lot of times misinterpret. Down here is always going to go the value on that axis is always the values of the variable. Okay, and so we have numbers that go from 5 to 65, and so probably the way I would represent this is that I would put here time to commute, and I would put it in terms of minutes, and I would say, okay, this started 0, and then I would say I'll probably go by tens. I'd probably make the bins 10. So what do I mean by bins? Well, what happens with a histogram is that things, the data, sort of gets grouped together, and so a lot of times this data will not be shown individually because that would really be a poor graph at that point. So we go ahead and group these into intervals. Okay, and so and then you could, on this axis, you can either put frequency, you can put the proportion, relative frequency, you can put percentage, whatever you want to show. Okay, or to somebody else, or what do you want to learn from the data? Okay, so let's take a look at a histogram then for this data. All right, here I put the frequency, but again, you can put whatever you want. Proportion, percentage, whatever. And notice here we have our intervals 0 to 10, 10 to 20, 20 to 30. So you might be asking, there's an obvious question here. Well, let's go back to the data for a second. You might be asking, well, where do I put the 10? Where do I put the 50? Okay, well, because they fall right on one of these stopping points here. Okay, so where do we put that? Well, what every stats book will tell you is that you put it into the higher one. So if we could go back here, this bar right here represents 0 to just less than 10. 0 to just less than 10. This bar right here will represent 10 to just less than 20, and so on and so forth. All right. So if we go back to our data, this 10 right here, okay, didn't go here. It actually went in the higher one, and then the 50 didn't go here it went into the higher one. Okay, so this one right here is 50 to just less than 60. So the 50 would have gone. That's why we have one observation there. Okay, notice there's no other 50 number in there. There's nothing from 51 to 59. So that's why we have one observation right here. Okay, hopefully that makes sense. Okay. Now, there's one other way that you can maybe see a histogram. And so when you have data that, say that you have a bunch of data like 0, 1, 2, 3, 4, and there's not a lot of variety in there, okay? And they're all kind of clumped together. The way you could also see a histogram, and don't freak out if you saw something like this. Let's say that you saw the hash marks, something like this, okay? And so all this is saying is that if you saw a histogram like this, is that you have, and you should know your data pretty well. And so if you know that you just have a bunch of zeros, ones, twos, threes, fours, and fives in your data set, and you make a histogram for it, and you see something like this, basically what this is saying is that there's 5 zeros, there's 6 ones, there's 8 twos, there's 5 threes, there's 3 fours, and there's 1 5. Okay, so if you see something like that, don't freak out. That could happen too. Okay. All right. We're going to see histograms quite a bit this semester. Okay. Now I want to point something out to you. Is that later on in the semester, and not too far in the future here, we're going to start seeing graphs that I'm going to sort of have these smoothed out curves. And so when I start drawing these smoothed out curves, and it doesn't even have to be like this bell-shaped curve here, it could be another form, but when it's nice and smooth like this right here, I'm drawing a histogram. I'm just not drawing all the rectangles here. And so what I mean by that is that this will be a little hard on the computer, but basically there's these bars here that I'm just not drawing. Okay, so when you see these smoothed out curves like this, you should think, oh, okay, there's a histogram underneath there, and there's a bunch of bars. He's just not drawing the bars. Okay, so we're gonna see that later on here. Okay, let's move on. How about a stem and leaf? So here's our data again. Okay, and so what happens with the stem and leaf is that, I didn't mean to do that, but that's all right. So this right here is the stem portion, and it represents, I got to take it back to about, I don't know, second, third, fourth, I don't know, whatever grade, when they talked about like the tens place and the hundreds place and the thousands place. So this right here, the stem represents some sort of one of those units, okay? And so if we take a look at our data, we know that this should probably stand for the tens place. But if we had data up here that was in the hundreds or the thousand, well, that means the stem would be in the hundreds and the thousands. Okay, and so and then you represent basically the last number in the actual number on the stem and leaf. Okay, so let's start with 10. And so we have to represent 10 on this graph. So every one of these numbers is going to be represented on the graph. So unlike the histogram that sort of clumps things together and you don't see individual values, you actually see every single individual value here. Okay. So let's see. So 10, we have a 1 for the tens place, and then we have 0 for the last number. And so I think we would go ahead and put, to represent 10, we would put a 0 next to here, and you say, oh, okay, so that's, put those two together, you got 10. How about 50? Where would you put that? I think we would put it down here, right? And so 50. Okay. And then 11. So how are we going to represent 11? So we already have 10 right here. Okay, we have to represent 11, and so the next number for that starts with a 1, it's going to have to go here, and so we're going to place a 1 here. So the way you would read this is that, you have two numbers here. You have 10 and you have 11. Okay. So notice up here you have two 26s. All right. How are we going to represent that? So first you have to represent both numbers. Okay. And so 26 shows up not just once, but it shows up twice. Okay, so you have to write down. So this is not 266. This is not 66. This is 26 and another 26. This is 10. This is 11. Okay, and so I'm going to go ahead and put all the numbers in there. And notice that things are going to shift a little bit. And so notice if you notice here that the 66. The 6 and the 6, I should say, the 26 and the 26, I said that wrong, is shifted out here now. And so what happened is that for a stem and leaf, we should put these in order, and the computer's going to do that for us. And so we had a 21 and a 22 and a 23 that went before the two 26s, okay? And so they're going to get shifted over, okay? So these leaves here, okay, these are the leaves, should be in some sort of natural order. Okay. So, how else could you see a stem and leaf? You could see a stem and leaf like this. Okay. And now this is out of StatCrunch, and you're going to use StatCrunch in the computer lab. So this is the same data. Okay. But the way StatCrunch decided to do it is just sort of divide things up a little bit. So it has a 0 here, and then has a 1. And so so basically what it's doing here is that it's in this one, since it has 2 1s here, it's representing basically all the numbers from 10 to 14 here, 15 through 19 here, then 20 through 24 there, 25 through 29, and so on and so forth. And so don't read it any differently. This would be 5, 7, 10, 11, 15, 17, 19, 21, 22, 23, 26, 26, 29, so on and so forth. Okay? So, the computers have different algorithms that it uses to figure this stuff out and how to break things apart. Okay, well, sometimes we have to adjust a little bit to it. Okay, personally, I would have liked to have seen it like this, but fine. If the computer did it like this, it still serves the purpose. All right. So, what I want you to do is I want you to write out the numbers for this data set. I want you to pause the video and make sure that you can write out all the numbers for this data set, because even if you get one wrong, it's going to show up on the test incorrectly. Okay, and so shut this off for a second, the video, and then come back when you've written everything out. So hopefully you've written everything out. All right, and so it looks like here's our answer. So we have a 0 and a 0. Okay, that would represent 0. And then we have 4. Okay, and we have 10, 11, 11, 14, 19, 20, 21, 23, 23, 27, 29, 34, 35, 39, 46, 48. Now here we don't have anything. Don't make anything up. Okay, there's nothing in there for 50. Okay, do not put 50. If 50 was in there, there would be a 0 here. Basically, they're saying the stem and leaf here is basically saying there was nothing in the 50s. Okay, and so notice there's nothing in the 50s over here. And then we have 63. Okay, and then maybe you could use that data for to calculate some other stuff that we're going to do in this chapter. Okay, so stem and leaf, reading it. All right, how about a dot plot? So now it's time to make a dot plot for our data that we had before. Okay, and so I'm not going to do this piece by piece. Basically, what's going to happen here is that we're going to go ahead and have a number line that goes straight across like this. Okay, again, our values of the variable here, and each observation is going to be represented by a dot, at least for smaller data sets. And so if this starts at 0, okay, and then we have 10 here, we would go ahead and say, all right, we have a value of 10, and we're just going to represent it with one dot there. Okay, 50 may be way out here, we would put a dot out here at 50, and so on and so forth. Okay, so let me get rid of that. That's a little messy now. Excuse me for having to do this. That's okay. Clean it up. All right, so we've cleaned it up a little bit. All right, and I didn't mean to do that. I meant to go back to get my pen. There we go. And so notice each dot now is represented each number is represented with a dot. So we have one at 10, we have one at 50, we have one at 11. Now notice here 26 is represented twice, right? And so we have two dots, okay, at 26. Okay, so as you get more 26, okay, we just keep on going up and up and up and up. Okay, so if you had more 50s, so the second 50 would go here, the third 50 would go here, the fourth 50 would go here, and so on and so forth. Okay, so now how else could you see a dot plot? So for larger data sets, notice up here it says up to 5 values per dot. Okay, and so what it's trying to say here is that, well, okay, these dots right here, this is for a larger data set, and so this isn't just for individual values now. Okay, these values are pretty close to one another, maybe. Okay, they may not be exactly at 18. Maybe this is 18.2. This one is 18.4. This one's 18.3. Okay, and so on and so forth. All right, so the values are pretty close to one another. All right, and each dot, every time you basically see a dot, you're going to see it's about 5 values there. And so a dot plot, the computer can adjust to very large data sets by sort of scaling things. Okay, so this might say up to 10 values per dot or 100 values per dot. Okay, it just depends, and the computer will scale appropriately. All right. So before we get into this, basically, I would use histograms just about any time. That's fine. Dot plots are pretty good for large data sets because the computers can adjust appropriately, and it gets a little boring though for smaller data sets. I don't know how much that tells me about the data set when I see, just a row of dots like that. And so I probably would have gone and probably made a stem and leaf or a histogram for this data set here instead of a dot plot. And so I would say if you don't like one graph, go ahead and make another one until you get something that looks good. All right. I'm not going to test you saying, okay, here's a data set, which out of these, histogram and stem and leaf, and which one is the best one to make. No, that wouldn't be a question. A question I might throw at you is that, let's say that we have heights of males, okay, and so it's quantitative, and I give you 4 graphs. I say, okay, which graph is appropriate for that data? I'm not going to give you 2 graphs that are both for quantitative data. I would only give you one graph that's for quantitative data, and you need to pick that one out. Okay, so I'm not going to make you choose between 2 quantitative graphs, because why? Well, that's kind of silly to memorize. If you don't like the graph, well, make another one and a different one and see if that works better for you. That's all. All right. So shapes of data. Okay, so shapes of graphs, and I'm going to show these as histograms. Okay, now this is for quantitative variables only. Okay, this is only for quantitative variables. Why? Well, remember, for the categorical stuff, I can switch. Remember, I could have easily switched out freshmen and put freshmen over here, and sophomores down here, and seniors over there, and so on and so forth. And so, however, you can't change a number line. Okay, and so believe it or not, these shapes of data actually is sort of the beginning part of data analysis. Okay, what kind of shape do you have with regards to your quantitative variable? All right. So the first shape of graph that you can get is bell-shaped. Okay, and that has a certain characteristic, is that it's symmetric. And what does that mean? It's that if you drew a line straight down the center of it, it looks the same on both sides. Okay. Now this right here was for sample data. Now I want to show you something. It's that this is not perfectly symmetrical. If it was perfectly symmetrical, this line right here, okay, would actually have lined up perfectly with that one. This one would have perfectly lined up with that one, and so on and so forth. Okay, so notice it's not perfectly symmetrical. Okay, so for real data, okay, you're going to have these bars that, maybe you have another bar. This bar actually went up there. Fine. Okay, and maybe this bar went down here, and maybe this bar goes up like that. Okay, and this one fell down to here. that is all fine for sample data. That's perfectly acceptable, that it doesn't fall into a perfect bell-shaped curve. Okay, so what I did here is I overlaid an actual true bell-shaped curve. Okay, and notice that the bars don't match up perfectly. See, the middle of the bar should match up to this line right here. Okay, so in some places it does, in other places that it doesn't. Okay, and that's okay. This we would say this is bell-shaped. Okay, you can even have a small little tail here. So notice that there's a little bit of a tail here. You might even have a little bit more of a tail here, and that would be okay. So that's approximately symmetrical. Okay, approximately bell-shaped. And that's what you're going to get it from real data. Okay, these aren't real data. Isn't models. Models could be perfectly symmetrical. Real data, okay. All right, so we have bell-shaped. That's symmetrical. What else could we have? We could have skewed left. Okay, so with skewed left, here's our histogram, and notice here that this graph is being pulled out this way. Okay, and so to even extend it out, maybe this graph, if I got enough data here, that maybe it could even be skewed out even further than this. Okay, so we have skewed left and skewed right, and so how do we know which way is skewed left or skewed right? Is the way the tail is pointing. So down here, the graph is being just sort of pulled this way. Okay, it's being pulled to the left, and that means it's skewed left. By the way, when could we get data that is nice and symmetrical and bell-shaped? A lot of times when Mother Nature sort of takes over. So like if you went ahead and made a histogram of, say, adult males in the U.S., and you made a histogram out of it, okay, it's probably going to be bell-shaped. Okay, and what does that mean? What that means is that we have a lot of data. Okay, we have a lot of data here in the middle, and so a lot of people are sort of towards the middle. And then you have a couple more people out here, less and less out here and out here. Okay, and so when you have bell-shaped, you have most of your data right here in the middle. Okay, right here in the middle. Here with skewed left, you have most of your data over here with larger values. Okay, so with skewed left, you have people or things that have larger values, and then you have data out here that is smaller in value, and you don't have many of them. Okay, so that's what's going on with skewed left. And so let's see here. What would be a good example of skewed left? Probably if you went ahead and put in test scores into a computer. So if you had a fairly large class, let's say a class of maybe 100 or 150, and you put in test scores into it, what you're going to find out is that we would have had to change the scale here, but let's say the scale went from, let's say this was 100, this was 80, this was 60, this was 40, this is 20, this is 0 instead of 0.2, 0.4, and so on and so forth, right? So what we would find out normally with test scores is that a lot of people did fairly well. Okay, they're going to fall over here, and then it's just going to drop off over here. Do you see many people that get 40s or 20s or whatever? No. And so you probably, if you took a look at test scores, it would be skewed left. How about skewed right? So here's a data set that's skewed right, and so notice here the tail is pointing to the right. Okay, so we have skewed right data, and so what's going on here is that you have a lot of people that have smaller values. Okay, so you have a lot of people with smaller values, and you got just a few people with larger values. Okay, now here was my scale before, when I created this graph. Okay, but maybe you can think of this as maybe age of college students. Okay, and you change the scale here. So let's say that you started at, now this axis doesn't have to start at 0. This one can start at whatever number that you want. It's this axis that has to start at 0. So this one, maybe you would start at, say, 16, because we do have high school students taking college courses, okay, and they're part of the university. And then you have students way out here that are maybe like 50 or 60 years old that are taking their courses. But do you see many of them? No. But are they on campus? Sure, right? They're taking courses. You're just not going to see many of them. So you see a whole bunch of people that are 18, 19, up to about 23, then it starts to drop off, the age, right? It starts to drop off, right? And it tends to be skewed to the right at that point. Okay. All right. So this slide right here, this was a slide from the authors of the book, and so it just tells you like lifespan is skewed to the left, and so let's say that this is 0 here, and this is say 100. Okay, lifespans tend to be skewed to the left here in the United States, and so you don't have many babies that die. Okay, and unfortunately that's what would be happening over here, but that's why the graph is so low. Okay, then as people get older, what happens? They're so they more of a chance to die, but what happens is that their lifespan tends to be pushed out. Okay, and so what happens is that you're going to have a big hump right here. Okay, with older older ages. Over here we have income skews to the right generally. Why? Because we have just a few people in the United States with extremely high incomes. Okay, they would be way down here, because then we have people that have 0. I don't know what's the highest, annual income. Let's say it's $100 million. Okay, and so you don't have many people over there either. Okay, and like we didn't have many babies dying too often. Well, over here we don't have too many people with that type of income. Where do we have most of our people? They make $40, $50, $60, $70, $80,000. Okay, so there's a whole bunch of people in there. Okay, between here and there, making that amount of money. And then you got your doctors, right? You got your lawyers and doctors and business owners, but there's not that many people like that. Okay, and so it tends to go down at that point. So skewed right. Last thing I want to chat about with regards to graphs is that we can identify what's called an outlier. So an outlier is basically an extreme value versus the rest of your data set. Okay, and so the graphs represent these differently, but you can imagine how a dot plot would look. If you had a dot, so this one's a histogram, and so with the histogram here, it just has this one observation way out here that doesn't seem to belong with the rest of it. Well, the same thing would happen with the dot plot, right? You would have a whole bunch of dots over here, and you just have this one little bitty dot over here, right? And the same would hold true for a stem and length, okay? And so outliers sometimes mess with statistical analysis, and so we have to be aware of them. Okay, and so these graphs help us identify the outliers. And actually what you might find out is that the outlier might be the most interesting part of your data. Okay, and so it might be a mistake, okay, but it also might be the very important piece of the puzzle that you're trying to put together with regards to the data. All right, so we'll talk more about outliers later, but this is one way to identify outliers, is just simply by taking a look at a graph, okay, and seeing, we have one observation that's really doesn't seem to belong, right? Now, it doesn't have to be high value; it could be a low value. So think of this graph right here, that it shifted to the right. So you have most of your data over here, and then you have, instead of having one little observation over here, you have one little observation down here. So outliers can also be low in value. All right, low in value, and so and you can also have multiple outliers in your data. And so if you have a very large data set, you might have 10, 20 observations that are outliers. If you have a data, and that's very possible in this day and age where we can have billions of observations in our data set, and so you're going to have more than one observation that is considered an outlier, and they're kind of sitting by each other. But boy, even if you had 20 observations here and you had 1 million over here, well, that's telling you that you got 20 outliers then because they're all sitting by themselves compared to the million that are sitting over here. Okay, so I think that ends this this section. All right, good day to all of you. Thank you.